Welcome to today's episode, where we'll be diving into the essential topics of database recovery and concurrency control. As data management grows more complex, it's vital for developers and system administrators to grasp how databases maintain their integrity and efficiency. So, let's explore the strategies and algorithms that ensure data reliability after failures and allow multiple transactions to happen simultaneously without sacrificing accuracy. At the core of database management lies the need for effective recovery mechanisms that can restore data after unexpected crashes. One of the key players in this process is the use of compensation log records and checkpoints. These tools are crucial for maintaining data integrity, as they provide a structured way to log changes and restore the database to a consistent state. Logging, in particular, serves as the backbone of recovery strategies. It's essential for tracking the changes made to the database. When a crash occurs, the system can refer back to these logs to figure out which transactions were in progress and what changes need to be rolled back or reapplied. This process is vital for ensuring that the database remains accurate and reliable. Now let's turn our attention to the policies that govern how and when changes are flushed to disk. Here we encountered two important concepts: steal, no steal, and force, no force policies. These policies determine whether changes made in memory should be written to disk immediately or held back for later. The steal policy allows the system to write changes to disk before a transaction is fully committed. While this can boost performance, it may complicate recovery efforts. On the flip side, the no-steal policy ensures that changes are only written to disk after a transaction is committed. This simplifies recovery, but can have an impact on performance. Then we have the force policy, which mandates that all changes must be written to disk immediately upon transaction commit. This guarantees that data is always current, but can slow down performance. The no-force policy, in contrast, permits changes to be written to disk later, enhancing performance, but requiring more complex recovery mechanisms. Understanding these policies is key for database administrators as they navigate the delicate balance between performance and reliability. To illustrate the recovery process further, let's talk about the ARES recovery algorithm, which stands for Algorithm for Recovery and Isolation Exploiting Semantics. ARES employs a three-phase recovery process: analysis, redo, and undo. In the analysis phase, the system scans the log to identify which transactions were active at the time of the crash and assesses the state of the database. Moving into the redo phase, the system reapplies changes from committed transactions to ensure that all completed operations are accurately reflected in the database. Finally, during the undo phase, any uncommitted transactions are rolled back, ensuring that only valid changes remain. The ARES algorithm is a powerful tool that helps maintain database consistency and integrity, even when failures occur. Now, let's shift gears and explore concurrency control techniques. These methods enable multiple transactions to operate simultaneously without interfering with one another, which is essential for maintaining data integrity while maximizing system performance. We'll discuss three primary concurrency control methods. First up is optimistic concurrency control. This approach assumes that conflicts between transactions are rare, allowing them to proceed without locking resources. They validate their changes before committing, and if a conflict is detected, the transaction may be rolled back. This can lead to performance gains, particularly in environments with low contention. Next, we have multi-version concurrency control. This strategy maintains multiple versions of data items, allowing transactions to read from older versions while new updates are being made. It enhances read performance and reduces contention as readers do not block writers and vice versa. Lastly, there's pessimistic concurrency control. This method locks resources before a transaction begins, preventing other transactions from accessing the same data until the first transaction is complete. While this ensures data integrity, it can create performance bottlenecks due to increased waiting times. Each of these methods has its strengths and weaknesses, and the choice often depends on the specific requirements of the application and the expected transaction load. A critical concept in concurrency control is the idea of serializable schedules. A serial schedule executes transactions one after the other, ensuring correctness but potentially limiting performance. In contrast, a serializable schedule allows transactions to run concurrently while maintaining the same outcomes as a serial execution. Striking a balance between performance and correctness is vital for efficient database operations. Achieving serializability requires careful coordination among transactions, which can introduce additional complexity and impact system performance. However, the benefits of allowing concurrent execution while ensuring data integrity make this an essential goal in database management. We also need to touch on isolation levels, which define how transactions interact with each other and the visibility of their operations. Isolation levels range from the strictest, where transactions are completely isolated from one another, to the most relaxed, where transactions can see uncommitted changes made by others. The choice of isolation level affects both the consistency of the data and the performance of the system. Higher isolation levels provide greater data integrity, but can lead to increased contention and reduced throughput. On the other hand, lower isolation levels may enhance performance, but come with the risk of introducing anomalies like dirty reads or lost updates. As we wrap up this episode, we've navigated the intricate yet fascinating world of database recovery and concurrency control. From understanding the importance of logging and recovery policies to examining the Aries recovery algorithm and various concurrency control techniques, we've highlighted the critical balance between performance and data integrity. As database systems continue to evolve, mastering these concepts will be essential for anyone involved in data management. Thank you for joining us today. We hope you found this discussion enlightening and informative. Be sure to tune in for our next episode where we'll continue to explore more topics in the realm of database management.